Uh, I think we are live now. So let's just start the live stream in Twitch as well. And I hope you can hear me clearly. I hope you can hear me crystal clear. At least I want it to be a clear. I want to be hear me clearly. So let's just see whether we are live on Twitch. Yeah, we are live on Twitch. We are live on YouTube. Cool. Okay. So yeah, we are live in both platforms, and oh my god. Mm-hmm. 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 Oh my god. Let's just leave it this today, and let's just see how. Okay. Okay. So today, in our previous live, we just you know, I just said this about we are going to write GPT2 in Rust, but the thing is, I stumble around with this Rust for GPU implementation. Let's just put aside CPU implementation for now. Let's just talk about GPU, and it turns out GPU implementation is not that easy. I think in Rust, it's because yeah, some of the thing like cust and burn, these kind of frameworks are exist for GPU programming in Rust. You can cust is basically CUDA binding or something like that, where you can program in Rust instead of C++. I mean CUDA. So so that's what it is. But for CPU implementation, it's much easier than the GPU implementation. We don't need to worry about any of the stuffs. We need to know is all we need to do is just code the architecture, nothing more than that. So we are good to go. But for GPU, it's a different story. Is because there is, yeah, there is bunch of them, but not very standard and very stable as C or C++ binding in Rust. It's still in Rust in the GPU programming or GPU. These sort of stuff is still not matured, and yeah, we do have APIs, but that's still experimental, and you can do stuffs, but um, it's not a production grade yet. I think as far as I know, Burn is good, but it's still not a production grade, but it's good. And so for today, what we are going to do is that I just build this GPT for CPU version, and let's just see how far we can go with this. And once we build this, and maybe we slowly add uh, GPU integration, and if not, maybe we can use C or C you know, the normal CUDA for GPU, and maybe we can connect it with Rust, or maybe we can still wrote entire code in C++. So that's one of the interesting project, but it's already exist. You know, if you are not if you don't know about this, I can just show you something. So this is the person who wrote this, I mean, created the project. And so it's a bit of a complex project. It's he wrote everything in C. So here you can see this thing is CPU version. So that's it. It's about to, I think it's about to uh, 1,182 lines. So that's it. So this is the entire implementation in a single file. It do have some of the dependencies, I think. You can see that here, some of the dependencies for tokenizer, data loader, and utilities. So nothing more than that, but the entire logic is he wrote entire logic in a single file. It's much faster and convenient. And other thing he wrote is this file called GPU train.gpu to FB32CU, which is this file. And this file is not that easy, because there is a lot of CUDA code, C++ code. Is because they wrote specific custom kernels for matrix multiplication. As far as you know, that's what they did. But still, some of the improvements you can do, maybe there is a lot of libraries by NVIDIA, which is much more stable and optimized, efficient for matrix multiplication. So you don't need to write everything by yourself. You can do some of the stuff. You can take some of the stuffs from older libraries like Kudian and something like that. They have a really good implementation for it. And if you want to some specific sort of thing you wanted to do with your GPU, and you can write that as well using CUDA. And remember, this all the things are only specific to NVIDIA GPUs, not other type of GPUs. If you have any type of any other GPUs, this type of code won't work. So you want to keep it that in your mind. But if you want to do something like these kind of stuffs in other kind of GPU, you can do, you can search for their software platform. And I think it is ROC, something like that. It's equivalent to CUDA for AMD GPUs. And um, but as far as I know, CUDA is one of the best and very mature, and it had been around decades, more than a decade, and so it's very stable and powerful. So so this is the GPU GPT implementation for GPU, uh, and so now let's just try it small. Let's just now we are going to do is just build a small version and build more and more complex thing top of it. um, but for GPU connection, I'm not sure still whether we are going to use Rust. So the whole reason for this live stream, or this video exists, is because Rust have some potential, and Rust is a much bit of a complex language, and there is so many basically so many promises about Rust. So that's why I just started this project. It's not um, it's not because any it's because it has some potential. So if not, maybe we can switch track with C++, those kind of things as well. And for now, let's just wrote implementation in Rust for CPUs. Okay. So yesterday, I just show you this code. It's actually I'm not the one who wrote this code. I take this code from Gemini. So 2.4 model. I prompted the model to something like a generate a simple GPT-2 model in a Rust or something like that. So it's gave me this code, and it's not that hard. It's very simple, but it do have some of the technicals. So we can go through bit by bit. And so this is a tensor class where we are implementing our own tensor, and basically we are using struct for it. So struct is much more convenient for the custom data types, and so we using struct. If you are in Python, if you are other class based language, you can create this for using class, define some class, and you can you know you can basically define these special methods, where if you're using a plus sign or minus sign, any type of operators, those those methods are basically called um, behalf of yourself. Um, that's those things are called, basically you can wrote basically you can override those special methods, like operators, plus, minus, and division and multiplication. These are you can override the methods for them. So so in other languages it's much more easy, but in Rust it's a bit of a complex, but not that hard. But you can see a lot of stuffs. So here we are just implementing the tensor class, and so this entire part is basically for methods. What are the methods we are going to have in this struct type, so in this tensor type. So here we have a new, basically for when you created a new is basically for create a um, data type in this actual assigning a data type in this assigning a data to this data type. So when you do something like this, maybe I can give you an example, or let's just see. Oh my god, I'm just typing with my laptop default keyboard. It's kind, sorry for the noise. So it's kind of a bit of hard to maintain hold the mic and um and no type. It's a bit of hard. Okay, no problem. Let's just, I hope you are not okay, not hearing that much of a voice. I can see the wavelengths, and so here I can see if you if you do like this. That's it. So now you are calling this method, and you want to basically send two arguments for this method. Uh, so the shape of the function, I mean shape of the actual tensor. What is the shape? And maybe it's need to be something like this. Okay, it's need to be something like, actually it's not a, this is okay. Here you can mention the size. So let's say you have some sound comma summon or something like that. It's if it is a 2D. And another thing you need to do is this, and the data. So the actual data is you need to send here, and something like let's say I have a variable called data. So this is the actual data where it's stored in a vector 32 type. Okay, and then this new method will take that and assign return a tensor type, and copy all the data and put it here, or something like that. Okay, so it's very simple. It's going to be written the self actual, it's going to be written the tensor type, and it's first it need to check that both of the thing, the size of the thing and the size we mentioned are equal. If not, it's going to be panic, basically stop the program. If everything works fine, then this code this will be returned, basically the self and the size and the data. Okay, the another method we are here we are defined is that zeros. Basically when you call a zeros, and you basically you need a basically you want to create a tensor type in our, let's say you want to create a tensor type, and you don't want to assign any data, but instead you need to instead you want to fill all the entries in the tensor type with the zero. So if you want that, you can call this method where all you just need to do is, it's kind of okay, let's just take this. So for now, let's just see. All you need to do is call this method. So you don't have to worry about anything other than that. So then you need to send a shape, nothing more than that. And every entries in that tensor type array going to be have a 0. So that's for this, and this is it's a kind of a special method, which is, you can see, helper to get the data as a 2D slice for the matrix. So it's let me explain. So here we have a here we are taking a here we are taking the actual tensor, not actual tensor, but reference of the tensor. So this is going to be read only, not a write. But wait a minute. So this is a slice. So we are going to return a slice of a vector, slice of a vector. You can call it this way. Maybe you can think of it as no. It's not a slice. It's going to be a vector where inside of it there is bunch of slices of other vector. So maybe you can think of it as it's going to be it's a vector containing another vector or something like that, another vector address or something like that. So first it need to check whether it's having a size of 2, which is a 2D, and if it is, then let's assume a chunk block where basically, so this method is basically for if we will use that we will use this in a future, but now for now let's just let's just create a chunk block, a variable called a chunk size. Then you are basically taking the first entry, which is a column of the matrix, okay, column of the tensor, and you have here, what you are going to do is get those it's kind of like you can think of it as where this chunk is if you have a flat array, let's say if you have a flat array and you are going to take a chunk of it, if you let's planning a 3 then and stack it together in let's say you have a 9 elements. Okay, you can stack them in a 2D array with a 3 into 3 size, right? So it's going to be a line element, 3 row and 3 column. So that's what it's actually doing. Take those chunks and collect them and order them in a row wise. Okay. um, if you let's say if you have a 4 comma 4 matrix and you wanted to change it to something like 8 comma 2. So if you want to something like 8 comma 2, you need to basically you are specific this you want to specify this parameter. So and you can take the second entry and take chunks of it. Let's say first before we have a first element, first row, and first row have 4 elements. So now after so what we are going to do is take a chunk of it, which is 2, and take them, and the second chunk is basically put it below the first chunk, and the second row and the second chunk basically put it below the second row, and the third row and the third row second chunk basically put it in below the third row. I mean yeah, third row's first chunk. So this is how it works, and then you are going to end up in a 8 row with 2 column. It's going to be, but this will work as long as as long as your desired size, and as long as your desired size and the exist and the size already you have uh, basically evaluate to the same number of elements. Yeah, let's say in this case we already have a 4 by 4. Now we have a 8 by 2. So if you multiply 4 by 4, it's a 16, 8 by 2, it's a 16. So we are end up in the same element. So in the same number of elements. If this number change, it won't work, right? So that's one of the important detail. And so that's it for this. It's very simple. Let me just so let me say this. It's a very simple thing, very simple tensor class implementation. It's not that hard. It's nothing more than that. Just we have a bunch of we have created a struct called tensor, and we have a bunch of methods with it for some operations. And this file is basically for let's just zoom this a bit so that you can see this clearly. So this thing is basically for operations, where here we have a very nice so let me explain this. So here we are importing the tensor class. Remember, we just created in this file. Here we are importing that. And another thing, what is this and where it is used? Let's just see. For now, let's just know this. Okay. Let, um, let's just see this, and let's just see this later. For now, we imported this. I'm not sure what it's for because I'm not the one who read this. It's you know that, right? So now here we have a very simple matrix multiplication function where for yesterday in my previous live I just explained what are the things you need to know. You need to have in order to implement GPT-2 or any type of model. You need to have a data type. It's called a tensor. So whether you can implement your own tensor engine, or you can use the existing libraries, it's up to you, right? Now now we create a very simple tensor engine, and now we need to do some sort of operations on it, right? Without that, there is no what is the reason for it? Okay, for to create a tensor in the first place. Okay, we need to do some operations, and specific set of operations we have a lot of them. And I think it's very educational if you understand this, so that we can build more and more things top of it. Okay. My plan is not to just wrote everything and that's it. Wrote everything and implement that. My plan is not like that. For now, focusing more on understanding things than writing everything by myself. Um, is because I'm not very good at Rust. So it's not my it's not my it's a new domain for me. uh, Actually, I'm from a different domain, C, C++, C, Python, these sort of things. But it's really beneficial. And I'm not sure whether I have to learn Rust. But Rust is kind of getting famous now, and most people are doing Rust things. So why not? So that's why. Okay, let's just get into this. And this we have a basically for a function, basically for a matrix multiplication. So this is one of the very very simple and naive implementation you can see in order to multiply two matrix. It's very simple and very naive, very simple. So you can see it's first it's need to check both of the matrix A and B have a both of the matrix A and B are 2D. And And so in order to multiply two different matrix the same size, so you need to have you need to with the same dimension, you need to have this rule for basically first matrix, first row, the number of rows of the first matrix is equal to the number of columns of the second matrix. So basically we have a matrix A and matrix B, where first row, the number of rows it have is equal to the number of column B have. Okay, so this is for that. We are checking, wait a minute, so sorry, it's a first, it's sorry for that, it's a column, it's actually I just, it's my bad. So what I just I just basically said it wrong, is because is what is what is that is nah, it's not a row. First, yeah, the A matrix, the number of columns in a matrix is equal to the number of rows in a B matrix. Okay, do you know what I mean? So it's not a row column, it's a column row. And if you have a row column, you basically need to swap them. Basically need to put the B matrix first and then multiply with the A matrix or something. Okay, and this is basically for checking those conditions, and if we met these three conditions, we are good to go. We can multiply those true matrix, and this is a bunch of variables for keep track of their rows, columns, and you know, rows, columns. And this is for the result matrix, where result data going to be, it's going to be a vector, and we are just filling this 0 with the number of how much number, it's going to be n, m into n. You know, the you can now you can remember that m is yeah, m is m is what, m is the row, and m is the row, and n is the column of the matrix. So the resultant matrix is going to be basically it's going to have a number of rows in a matrix and number of columns in a B matrix. Okay, so that's for this. We are just filling the zeros with it, and and then here you can see the for extreme optimizations. This is where you would use SMM, SIMD, and the matrix like libraries like matrix multiply and parallelizations. So these are the libraries. If you want, you can use it. Still this is for educational and understanding purpose. So that's why we have this sort of very simple and naive implementation. Pretty soon we are going to have we will implement complex stuffs. Okay, so here we have some sort of a for loop, basically for accessing so the thing about matrix multiplication is you take a first row and the second row you are going to multiply with it, right? And and add the result to a single element. So it's kind of if you see it in a vector sort of thing, you can call this as a dot product. In a matrix multiplication, it's a matrix multiplication. Okay, so you're taking of a first row and the first column. So you're not taking it, just accessing from it, accessing the index, and this is the sum. Basically you're going to multiply the first row and first column, and you're going to basically multiply them and add in the single element and put it in the result data matrix. Okay, um, I think it's I hope you have a clear image of it. And the another loop is basically for where you're now you are basically access this now you are basically where access this first row and this first column. Now what you want to do is to now you need to go through this one by one and this one by one and multiply the according their index. Okay, so now for this loop it's basically for the row, this loop is basically for the column, and this loop is basically for um, accessing the index for both of them at the same time. Okay, so now you can see here this is a type data, which is basically um, a tensor. Let's just see. So this is going to be, remember, this is going to be our data type, custom data type tensor. So remember, we have a variant called data, right? Property called data. So this is the thing we are accessing here. And so the thing, another thing is that if you are in Python, you're going to be accessing a two index, and if you're probably in a two index, but if you're the Rust is kind of like you can access in our single index where the entire matrix is flattened out in a single array, and you are accessing the end index goes from 1 to the length of an array. Do you know what I mean? So it's basically you're not basically accessing let's say I have a third element, a third row, I have a third element in the third row and the fourth element in the third element, the third row, and it's basically third row and third column, right? 3 into 3, 3 comma 3. It's basically accessing the third row and the third column. Okay, so that's how basically most of the thing when it's come to 2D matrix, how we that's how we access. But in Rust you can access this way, something like actually this is remember this is actually V32 type, so it's going to be a single yeah, you can create them, but you can, in order to access them, you can imagine them as a single flat array where it's going to be the first element start at 0 and the end element start at the basically like the multiplication of your row and column, length of the row and length of the column. Okay, so that's how here you are accessing the element. So now remember, now we have a first row and the first column. We need to access the both element at the single loop where we need to access the first element in eighth first element in the first row of the A matrix, and we need to access the first element in the first row and the first column in the Bth matrix. Okay, so it's going to be and in the second element the thing where this is where thing gets bit tricky, is because when you access the second element, you can it seems like you can access the second element pretty easy, because you know in a matrix you have a first row and you want to access the second column, right? And in a B matrix you are not accessing the second column, but instead you are accessing the second row. So it's happened to be it's happened in a single, it's need to happen inside of a single loop. So for that that's why we have these kind of variables in the first place. We just created some of the variables for it. So here you can see it's I into k, basically meaning that so I, it's not going to be changed until this for loop is finished, right? So that means I'm going to stay in a first row, and the k int k means basically for first this thing is 0, right? And the k is basically the how much column, the length of the column, right? So it's basically for when this loop ends. So now you can access the first row is because I is 0. So anything multiplied with the 0, it's going to be as 0. So it stays in a uh, first row, right? But for next row, it need to be jumped to the second row. So when this thing changed to 1, this k thing is basically multiplied with that. So here, let's say I have a column of 4, then 1 into 4 is equal to 4. And here you can see it's jumped to the next thing. Is because remember this entire thing is flattened out, right? So the index is not going to be like 0 comma 1. Now the index is going to be, if we are end up in a second row, we are going to be we are going to have a element that the index of um, 4, right? The 4 is the first element of the second row, right? So remember, because we flatten out and we have a 4 column, and which is basically first 4 elements will be included into 0 to 4, 0 to 3. Then second 4 element is will be in 4 to 7, then 8 to then 4 to 7, then 8 to 11, so on, so on. Okay, so it's very convenient to for access that way. So here you can see that and the L thing is basically for how much we are in, how much where is the actual index in the row wise, okay, column wise. So here remember we need to go first row, first column, and the second column, and the third column, and the fourth column in the element in the first row in the eighth matrix. And it's you can basically imagine it's going to be it's going to be in a row, column wise, and it's going to be in a row wise. So that's why we are doing this way. And for B we have a L. So L is basically we need to each time this for loop ends, we need to go through the next element, right? So it's need to here for the case of A, we don't need to jump the next row, we need to jump the next column. For the case of B, we need to jump to the next column, next row, sorry for that, next row. So for that we are just using this variable. So every time this variable change, and every time this variable change, it's going to be every time this loop give a trip, it's going to be in the next row and next row, something like that. That's why here we are using this. And n is basically for column and how much elements it need to jump. Basically we remember we have a flattened number. Now how we are accessing is 0 is the first row first element, right? And now we want a second row first element. So we are accessing 0, then we are directly jumping to 4, right? That's the, as I earlier said before, 4 is the second row first element, then we are jumping to 8. Okay, so actually it's a 8, 4 5 6 7, it's going to be 8. Okay, so on, so on, so on, something like that. So that's why we are doing this. Then once we ended single round, once we end up the single this loop, we are going to store that in this array. So sorry for smashing mic. And so for that we are just doing this like first row we are going to take a row, and it's going to be multiplied with the n, basically where the end up matrix is going to be n into m into n. Okay, m rows and n columns. And this I into m thing is m thing is basically where you need to first fill out the first row, and you need to once we finish this first row and first column, we need to jump to the first row and second column. Then where we need to jump to the then sorry for that. So it's not so it's basically for once we multiply the first row and first column, we need to store in a first entry. Then we need to then the second thing, um second the column thing, you need to jump to the second column elements, and each need to again multiply with that, then it's evaluate to a single value, then it's going to be end up in a second array. So that's how it works. That's where we are multiplying this. And because remember the once for this for loop is end, this is going to be started again. So after this only ends, the actual the I variable going to be changed, right? Otherwise it will not. So here you can clearly see that I is not going to be changed with this. So it's going to be stayed in the same array, right? Same row, sorry, same row. So that you can access the 1 2 3 4 number of elements in there, and assign their according sum to it. Then you finished. Once you finish this, you are going to send a jump in a second row when it becomes the one and the number of row something, and n is basically for now we finished this chunk of block. We are going to focus on second row, and it's going to be started. It's going to be started after I into n, 1 into n in whatever n is. Okay. Once we finish this, once we have the actual data, and we are going to, you know, basically now here you can see we are calling this new method basically for taking the data on the size and put it in our custom data type. So which is we created the tensor data type. That's it for matrix multiplication. Okay, wait a minute. Let's just see. Size and put it up. Okay. The another thing, I'll just focus on this thing. So it's a function where we are using this for activation function. So it's a Gaussian error linear unit, GALU, you can call it that way. It's going to be take this is the actual formula for it. Maybe we can search in just see. So this is the function. It's a silo. It's not. It's here you can see. So So this is the actual Gallo function. It's a bit different than ReLU. If you're familiar with the ReLU, that's also a good function. So here you can see that here, this is the ReLU function. It always have it will have derivatives in all the places except this place. I don't think it have, but Gilo, it's much smoother than the Relo, and this is how the derivative looks, right? Here you can see there is a cut, right? So this is where this thing is, and here you can see that the Relu function and Gilo function is much more smooth. So that is what it is, and so for that, for GPT-2, we are using Gilo activation. That's it. We are going to take the array and you know put it put it through this function. We are going to have activation. That's it. And we have softmax. Softmax is it's kind of a way to express if you have some kind of like matrix of numbers and you wanted to evaluate them to probabilities, something probability kind of thing, where so that you can understand them much more easily, which have more probability, which have less probability, so you can do a lot of stuff with that. So for that you need to have the softmax function, so where it's going to be take a bunch of normal floating points numbers and end up in probability, I think. So it is a bit it is a bit complex. Maybe we can show the formula. Let's just ask let's just ask just wait a minute. Let's just ask GPT. What is softmax formula and why we are using it? Softmax functions can convert a vector, raw vector source, which are called logits. Yeah, it's another name for it, into a probabilities to sum. Okay, so this is the formula. So for z vector z with the component of z1 to z, and the softmax of the softmax ith component is, so it's going to be like this. We're going to give a single element to this, and it's going to evaluate to e power z, e power the actual number, and the divided by the entire number. It's going to be sum the entire elements in the number, entire elements in the array. Okay, here you can you can easily understand this, right? E is base of a natural logarithm. It's a, you know, it's a E number where it's if you're really into this, if you're coming from a math background or who are interested in math kind of thing, you know this how it works. There is a lot of explanation for E. Um, Maybe what is the explanation? A lot of what is the you know what is the for formula for E here? The simply is so this is the actual number, the E number, but you can have a formula like this. This all evaluate to this, not exact number, but with some approximation. So this is also evaluate to the that, and but this is the actual number. There is some of the methods that evaluate to much more precisions. So this is the number. So that's it. So it is related to a logarithm. So maybe you can have log and a are related. Natural logarithm. This means 1 because e power 1 is equal to e, and more generally is equal logarithm of e power x equal to x. And if you put those in a logarithm of x, it's going to be an x as well. So this is how they relate. It's an inverse function. They are inverse function. It is basically if you do one thing, they will undo that. Let's just say if you evaluate e to power of x, then if you okay, then you take the x, take that value and evaluate to a logarithm, then that's going to be give the value of x. Why this matter in machine learning? I think that's how it done. That's how that's what it do. But so why this is matter? Um, but if you're not sure about this, you can check it out. There is a lot of guides. A lot of guides about a lot of things in mathematics. That is the thing about mathematics. One of the thing about mathematics is so much. It's really concise and very short and small thing, and it's going to be but it's but the thing it express is much more than that, right? So the formula or any sort of thing, any sort of e- equation or something like that, the number of parameters it have is much smaller, but the expression it's going to be the number of things it can express with that is much higher. That is why these formulas are um, they call it as a universality or something like that. It's hard to spell for me. Universality, universality, something like that. Okay. So this is the relation between E and why this is matter in software is create exponential difference between numbers, and cross entropy uses log. So this is the loss function we are going to use, and uses log to measure the distance between predicted probabilities, so and the actual label. So it's going to be take probabilities and basically find a single value about whether this model is predicting good or not based on the predicted probability and the actual label. So that's the thing we need to optimize here. We optimize this number, um, we have a model, good model, and it simplifies back propagation math. It's basically back propagation is a kind of a hard to spell. We can just say backward pass. Hmm. That's the another name for it, backward pass. So there is a forward pass and the backward pass. So gradient become linear in some places. Linear means basically you have a number and you do some operation and it's going to be written number, and that number it's going to be a multiplication of the first number. That's what linear means. Maybe here they meaning that the actual weight number and the gradient is going to be in a multiplication of the it's going to be in a relationship between multiplication, where you take one number and multiply with some number, you're going to pick up the gradient of each number, something like that. I hope yeah, I hope you have at least you have some idea about how this works. It's a bit of hard to talk for a in an unstopping way, and but okay. Now that we finished this, and let's just jump into the code. So that is basically about softmax, and it's a bit it is a bit, let's see here. Maybe I can explain that here. He built something like, it's not a microgad, it's he wrote something like um, so he have a much understandable, you know, much understandable softmax implementation. He wrote that. Um, going to be in the end. I cannot see any softmax implementation. Yeah, but yeah, he do. Where is it? Hmm. I know it's somewhere around here, but okay, let's just find it up and can you just implement socks? Here we are exponentiate that, right? We are taking the max and minus with every element and subtract with every element in that, right? And evaluate to each the number, then we are going to return the sum divided by each element. So it's a concise implementation, but actually what happened is here you can imagine like some kind of a for loop. It's going to be take each element and minus with the max and evaluate to the x e power x and divided by the sum of the array with the number, sorry, the x value with the sum of the array. Then that's what it is, I can see. So but in our code it's bit looks tricky. Okay, let's just ask GPT because I'm not sure about this code, how it's just explain this code. Sorry, it's not. Last dimension of the vector. Okay, tensor. It's going to take a mutable reference. Okay, that's fine. Modify the tensor in place applying this up. Okay, understandable. And this start thing, get the size of the last dimension and 2 comma 3 some softmax. Hmm. So the thing is, after you get the lodges, you are not going to evaluate all of the lodges to the probabilities, but you are going to evaluate. Sorry for that. You are going to evaluate them the last dimension of that. Basically, if you have a here you can see you have a two elements, but you are evaluating the only three last dimension. Okay, it's much simpler in Python. You can see that, right? It's a very simple. So because we are using this thing, even we are not using this NumPy library, we will in Python it's much simpler. It's going to be much simpler. Here it's clearly explaining that if it is exists this kind of data, it's going to be separated into chunks, and we are going to evaluate them. Then find the maximum value in that chunk of numerical stability. You are going to find maximum value in this and in this, and help avoid large expenditure that could cause overflow. Okay, subtract subtract basically subtraction and apply evaluation, then accumulate the normalization. That's it. We are going to then we normalize the each element. What is this? It's the start thing. It's is it representing that? What is this? Context. Dereference. Yeah. Here we have a nice example. Is the data and its address where B is borrowing them, and C is Okay, here we are borrowing the address. Here we are dereferencing the B. Basically mean here if we do this, it's going to be give the value of y. It's I32 itself, I32 itself. Retrieving the value, retrieving the value from the last dimension, but not the reference to it. That's it. And you have a layer normalization thing. Just explain. First, explain what is layer normalization. Normalization. It's kind of normalizing in the layer wise. Layer normalization is to technique the stable and accurate training, accelerated training of deep neural networks by normalizing the activation within the single layer. It's basically come from this paper. And why neural networks works better when input activation are normalized, meaning their values have mean of 0 and standard deviation of 1. This helps keep gradient stable. Basically where you don't have a high grade, you don't have a very low gradient or high gradient, something like that. You have some. So if the distribution is if their distribution have a mean of 0 and standard deviation of 1, it's basically um what is that, Gaussian distribution, I think. I just asked ChatGPT. So the key, gradient is much more stable, improve convergence. You can find the best set of solutions um, easily and avoid exploitation and vanishing gradient problem where basically when you are when you are doing the backward pass, the gradient is basically evaluated to 0. So basically there is no change happening. How normalization works all features in a single sample rather than normalization works normalizing all the features in a single input sample rather than across the batch like batch normalization. And this is another kind of normalization technique. Suppose input vector is x1 x2 x3 xn, and we compute mean. So we are basically compute the mean with this array in the and the standard deviation. So this is the mean, basically average kind of thing, and standard deviation. So this is the formula for it. Yeah, going to multiply minus the mean and square it and plus with the stability term. I don't know what is how they call this, mu. This is mu, right? This is omega, right? Okay, that is it. And this is the parameter, hyperparameter, I think. Yeah, trainable parameter. It's a hyperparameter. Transformers like GPT board learn is heavily used before. So I'm basically thinking that maybe we can just implement our own. Now we are doing this, but this code is not written by us, right? It's I basically wipe coded. Maybe you can say like that. I just basically wipe coded. I'm not a wipe coder, but I just wipe coded this, wipe coded this. So that's it for operations, and we have these kind of things. I'm not familiar with these kind of methods still yet. I know, but I know this heater and map and this kind of things, but the last, so it will give the last element or something like that, unwrap them. It's going to be get the value, but still I'm not quite good at these methods. Okay, for now these are the things we just want to implement GPT-2, and this is the model. So it's all very concise. Sorry for that. Do you hear any sound? Yeah, mic is clear. Okay, let's just get into this and wait a minute. This is okay. We have this. Sorry for that. Gemini. Where is it? Yeah. Wait a minute. This is the code. Here we are just implementing the one we just implemented, right? Here you can see the tensor and the operations we have just created, and represents the weights for linear. So again we are going to create another sort of like a custom stack, and we are going to use the tensor for it, where it's going to be have a data and the size. For biases the same thing, and we are implementing the for pass here for specific linear thing. Remember, we still haven't covered the backward pass thing. We are all the things we are doing is a forward. Okay. So here I can see it's a forward and a third taking the linear itself, and another thing is the data where we are going to multiply with it and returning the tensor, and this is the result, the actual weight with the multiplied with the data. Add biases to the each rows. Linear layers basically have a formula like wx plus b. Just taking them, multiply with the weight, and add the bias. Next we have a chunk, but it's result dot data dot chunk. Basically adding the biases for each element, so to say. And result the in matrix. Maybe I can show you a bit about linear cell line. So you know this is how this is the data points, and you want to model this data, and you are basically, yeah, putting a line in a center so that you can expect these values as much as possible, predict this value as much possible. That's what we are doing for a single node. There is a lot to cover. If we want to focus on this sort of things, it's you know still I'm talking about the high level, about deep learning and these sort of things, but there is so much in-depth and details we need to cover, uh, but for now let's go through this. But for but in future we will cover this as well. So another thing we are going to implement is a custom check called attention. So it's the actual attention. So we are going to have three set of matrix. The C attention is basically our combined QKV projection, and projection is output projection matrix, and N hat as and dimension. Embedded dimension is basically N hat is how much number of hertz in your attention. Basically it's a multi-hertz attention, right? It's going to be have a multi-hertz. And embedded dimension is basically the dimension of the embedding. I think for GPT-2 it's 768. Then we are implementing forward for attention, uh, basically taking the matrix and separate it into a three matrix, Q, K, V, and multiply with the Q, K, and V, and multiply Q, K, V. Okay, what are you creating here? Okay, yes, sequence length and the dimension. Okay, number of heads in a dimension is going to be divided by the number of. Okay, so that we finally end up in the same dimension. That's why the number of heads is divided by the dimension. Okay, you know what I mean? I hope you understand that. And this thing, get QKV as the basically we are calling forward on it. So which forward we are so it's going to be a linear, right? So here we are creating the linear thing, forward for it, linear forward, and we are going to call that and give it to the x, and it's going to be written the qkv, and then we need to um, split the block basically. Here you can see here assigning q data v data, then part data dot chunks embedded dimension. It's actually I'm not sure what you are doing. It's a data dot chunks. So we are setting the embedded dimension. Then we are going to use the part unwrap extend from up to the embedded dimension, then embedded dimension to 2 into embedded, then 2 into embedded dimension to 3 into embedded. I think they chunked them with the dimension, embedded dimension, then first chunk is q2 embedded dimension, then second chunk is embedded dimension to 2 embedded dimension, and so on. We are assigning each of them to these variables. This is a simplification. A real implementation would need to be transpose and resize tensor to separate the hertz. Let's proceed with the concept flow. Okay, that's what I'm saying. So I think let's just wrote our implementation by ourselves. Maybe tomorrow, maybe our next live. But for now, we are just you know understand this code in high level. Then we directly jump and wrote the code for CPU version. For GPU version, it's a bit of a complex thing to do, I would say. So this thing is actually a single unit, single node in the layer. Now we are creating the layer. So it's have a forward. Now we are entering into this. where a multi-dimensional array into multiple multiplied with the multi-dimensional array. Before that, it's going to be have a some kind of a scalar unit, and for a single node it's going to be a scalar and multiplied with the array. Now we have a bunch of scalars, so it's going to be array. Now it multiplied with it's going to be multiplied with the data, the x value. Here you can see we use the GLO, which is you know created in this apps. Here you can see it's all all build up on the hierarchical order where block have the MLP have the um, linear and linear have the tensor. You can see that others see the pattern, right? Attention have the linear. So it's sort of a we have a first the node and layer and the entire stack and a bunch of stack. It's a goes on something like that. Weights and biases the tuple for layer norm, then attention. So it's here you can see that first we have a layer norm, then attention, and then layer norm. So and MLP. It's kind of how they have that. So transform key touch. So where is it? So here you can see that actually it's come here, then we have a layer num, then we have a, let's just see here. Okay, so this thing is basically come from here, so we will not have this block and this block. We are going to have a single block. So the layer actual GPT-2 have in actual GPT-2 they switched this layer num to here, not here. So first they first the data go through this, then layer num, then feedward plug, feed forward is basically MLP, right? Feed forward, then linear and softmax. Layer num, attention, layer num, MLP, right? And the feed forward basically forward pass, where it's going to be contain everything here, everything about that normalization layer norm attention. Then it's a long line, isn't it? Then we create a hatch and h key, then layer norm, and then we create a hatch. It's basically okay, new tensor, okay. Then clone them, and again um, go through the layer norm. Then we have final layer with the MLP forward, and we have a MLP output, and then we create a new tensor with that output MLP output dot data, and we are basically do map on it. Map is basically where you have a you take each element, some modify it, and give it back. That's it. It's sort of very high level implementation, I would say. I'm not read this code before. Um, this is the first time I just prompted it and put it back and read it with you. Hey, how much time left? Oh my gosh. So just find a minute. So this is the continuous. There we are creating the GPT2, and we are going to be you can see, now it is the same thing. We have a hierarchy, right? So block is going to be inside of the GPT2 tensor using the block, right? See, and that's it. Now we are doing the same thing with the multiple blocks. Once you finish this final layer norm, then we have a logits, and we return the logits, and it's not that complex. You're getting sequence length and embedding dimension, creating initial tensor from the tokens, and the positional embeddings where we need to create um, um, a sort of vector for each tokens and each positions. creating them, assigning some value to it, and then adding them, and then we have a single render state, and we are going to take this and do it to the block forward. Then it's going to be go through layer norm, attention, layer norm, MLP. Then when it's come out of the final, it will go through the final layer norm. Then it will go through the last uh, uh, linear layer, and we got now we got the logits, and this is the last file. So here it's at sorry for that. Okay, so this is wait a minute. Load the pre-trained weight from the file. Popular GPT, and this is not a trivial step to and actual weights. Give get input tokenizer from the tokenizer and run the forward path. Ooh. Okay. So this is for pre-trained weights where you are getting download this weight from the location, and as through this, if you don't want that, maybe we can just start our GPT implementation here. We do need to have this tokenizer thing. That's the part we need to take care. But for now, it's a high level structure. Maybe tomorrow, maybe our next live, we are going to implement uh, this. We are going to implement this from sort of like actual engine where still now we haven't touched the backward pass part. It's much more complicated than this. So maybe to next live we sort of just implement some sort of a higher backward pass, or maybe we can just really get into the implementation part for CPU version. Maybe for GPU version, maybe we can get into the CUDA part. Okay, that's for today, and this is how you can implement GPT. Not only GPT, any sort of models are mostly nowadays relies on this sort of architecture transformer where attention, MLPs, and activation functions, softmax, and you can see this a lot if you're really into deep learning. That's how that's the one of the state of the art approach to achieve AI. So AI is not um, it's not a single thing where deep learning systems are AI, artificial intelligence systems, but artificial intelligence systems is not only a deep learning systems. There are a lot of other algorithms you can that are not deep learning things, and but for now deep learning systems deep learning is kind of a working really fine, showing potential results. And current LLMs are deep learning systems, and maybe in the future, maybe we can see a lot of other types of algorithms as well. Um, but for um, but for our current time, we are mostly rely on these deep learning systems, neural networks, sort of things. And it's hugely rely on data. And it's kind of a supervised learning too. There is a unsupervised learning, but semi-supervised learning, but they are not showing much of a potential. I'm not sure about that, but there is a lot of active research going on those kind of area. And one of the other thing is a very powerful method for AI is a reinforcement learning. That's the actual magic where you can, there is a lot of magic there. Basically, you can have this sort of you know how I put this, where you can have this sort of assistant system. In my previous live I just talked about the sports training. Those are really depend on reinforcement learning techniques. And so that's how today um, AI is working. Okay, finally, you can choose something which is that. This is how looks CUDA code. It's not a exact C code, but it's a C kind of a code. But it's specifically for GPU thing. So for Rust, it's not still very mature, but for C, it's not mature and stable. If not, maybe we can just, if we don't if we don't write as Rust in Rust for GPU, maybe we can just take a look at this for writing, and they sort of having a good implementation. So this is basically for uh, gradient engine AdamW. They do have a lot of implementation: attention backward, attention forward, and crash and entropy, softmax, crash entropy, and encoder forward, backward. They do have a ReLU. They wrote all of them, and it's a cool project, I would say. And And that's it. I hope um, mm, that's it for today. And let's I hope you learned something um, by watching our live. And if you like stream, do subscribe, like. If you want, you can share. And thank you for watching. uh, I'll see you in next live. Okay.